And introduce. Okay, so welcome everyone back. Today we are very happy to have Joerg Teschner from Hamburg, who is going to tell us about mathematical structures of non-perturbative topological string theory from Gromov-Witten to Donald-Thomas invariants. Please take it away.
Okay, yeah, thanks a lot. Thanks for the invitation. So it's a pleasure to be back in Berkeley, even if it is virtually. Right, so let's jump into the story. I mean, I believe in this audience, I can be very quick about sort of some introduction. So as you probably all know, the partition function of topological strings of interest both for physics and mathematics. So effective supergravity actions, string actions, and engaged theory, Nekrasov partition functions can be computed via the topological string. And in mathematics, there's a big story attached to names such as Gromov-Witten, Donaldson-Thomas, Kumar-Vafa about enumerative invariants of Calabi-Yau manifolds. And what I do want to mention in any case is that, of course, this has attracted a lot of attention in the past, and there's a lot of different approaches and formalisms for computing this guy. I think, however, it's fair to say that most of them are perturbative in one way or another. So let me name topological recursion, holomorphic anomaly, topological vertex, and so on, where one typically produces formal series in at least one variable. Some others are non-perturbative in some way, like matrix models, and there is a more recent series of developments of Marcos Marinho and collaborators, say, proposing a non-perturbative definition of the topological string partition functions. But anyway, what I will try sort of to motivate is that there's probably, even in simple examples, something left to be discovered. So let us go to a formulation of the problem, which is more precise. The object of interest is going to be the topological string free energy, which, okay, I don't want to elaborate this very much, but in the end of the day in our work, it turned out to be important to consider sort of both of the pieces it has. One is the constant map piece, which is just dependent on the topological string. And lambda, which is the formal series down here, where the coefficients are provided by the famous Gromov-Witten invariants. So that is an expansion in powers of lambda, as well as an expansion, well, of some formal variables q to the beta, where beta runs over the second homology of the Calabi-Yau we're interested in. And all right, so these are well-defined mathematical objects, and in this way, basically, we have defined the thing completely and rigorously. And that is sort of the starting point, but okay, it is well known that this series is divergent in basically any case. So the question that this raises is, do there exist analytic functions which have this formal series F, the topological string free energy, as asymptotic expansion? And if there are several such functions, how are they related to each other? In some sense, that's going to be the main theme, namely that some of the most interesting things are probably in the relation between different topological, different, say, non-perturbative definitions of this function, or, well, yeah, different summations, if you like. All right, so we will, however, focus on just a single and rather simple example, one where I guess you might think it has been studied to death and there's nothing left to be found there. So that is the resolved Koni fault, which has been probably used to check basically any non-trivial idea in topological string theory has been, I mean, it has been considered and tested in that particular case due to its simplicity. which gives us, well, a very explicit formula for this series F tilde, which is the part of the topological string free energy depending on Kähler moduli if we're sort of in the type A context. So for the resolved Koni fold, the expression is fully known in full glory, where we have as coefficients here some multi-logs of the QF, which is then exponential to pi I t, where t is the Kähler modulus. And the Kähler modulus, I mean, just for, I mean, I'm introducing here the geometry of the resolved Koni fold, which can be represented as toric geometry through its toric diagram, where then the parameter QF appearing here is associated to this intermediate leg. And yeah, this is a result going back to Gopakumar-Vafa and in math, Faber-Pantaripande. They have sort of provided the basic results leading to this explicit formula. So we have a very concrete object, a very concrete thing to look at.
You're usually, we wouldn't draw exactly that picture to go with a Koni fold, right?
You would draw what? I mean, what's the?
People would associate this like O minus 2 plus O0 bundle over P1, as you can see by sort of lack of symmetry. And it's like you'll draw a slightly different picture for the Koni fold, but
okay, sorry, I was. I mean, okay.
No worries.
It's true. I was slightly sloppy here, copying a picture which is close to what.
No worries. I just wondered if it was deliberate because the perturbative invariants are very similar, so they differ by like overall sign and free energy or something. Okay.
Yes, okay, so sorry, there was a slight sloppiness here, but in any case, this is the thing I want to be working with. All right, so here is sort of, well, if you like, the fully pedagogical part, namely a slide in slightly modified form taken from my complex analysis class a few years ago. So there is, of course, a well-known technique for turning divergent series into actual functions, and this is called Borel summation. So let me be quick, but nevertheless, maybe it's useful to recall at least sort of the key features, because that is going to be the main tool on which our results are based. Well, actually, maybe I was a bit quick in starting. I, of course, want to stress that this is a joint work with Muad Alim, Apan Saha, so initial was misspelled here, and Ivan Tully, who are all based in the math department, Hamburg University these days. Good, back to the Borel summation. Good, so here this series is divergent. That's our series we start from. However, it can happen, and it does happen in our case, that if you just divide these strongly growing coefficient, well, sequence of coefficients an by n minus 1, or here with the renamed index of summation k minus 1 factorial, that then you do get something that is convergent in the neighborhood of 0. And furthermore, may have and does have in our case an analytic continuation to an open set U, which contains nice rays, so rays emanating from the origin. And so this is assumption number 1, that we need to get started with Borel summation. Assumption number 2 is that then, with function that then is perfectly well defined, g of t, we can compute Laplace transforms like here, integrals like this, along that ray rho, which starts from the origin. So of course, again, there's a convergence issue. The function g has to have a sufficient decay and behavior maybe at t equals to 0. So if that converges for lambda in a non-empty open set V, then, well, we just basically add the 0 mode and define something, a function of lambda of that form. And it's a very elementary exercise that if you just plug in here the series expression for g of t and do the integration here term-wise, what you do recover is that, that formal series you started from. So that means here you have achieved a definition through this two-step procedure of a function which has a certain range of analyticity denoted V, and which has the divergence series we started from as a asymptotic series expansion. All right, and this is what we now apply to the case of the conifold series. And well, it works. And the main need is, of course, to determine where it is analytic and which rays we can use in order to make sense of that. And yeah, part of the most interesting aspects of the story is when this choice of ray is non-unique, because then there are multiple definitions of a non-perturbative completion or non-perturbative definition of that function. And well, this may be unsatisfactory on first sight, but in the end, sort of the most interesting information is exactly in the relations between different definitions. And that was going to be sort of the theme, the main theme here in our talk. But okay, let's be more concrete. Details don't matter so much, but on the other hand, but let me note that, well, there was a beautiful work of Paschetti-Schiappa, who found a formula for the Borel transform of that particular series that we started from, the one here. And well, for us, although, well, at least part of the story probably could have been done with their expression, but in the end of the day, I guess for the full story, we needed to first find an alternative expression, and that's the one here. So this is simply what you can compute with a few tricks, perhaps, by starting from this formal series here, or you can just by basically going backwards, that is Taylor expanding and integrating term-wise, check that this formula reproduces the formal series we started from. Okay, so let's have a look at analytic properties. So this function g of psi and t is, as usual, our Kähler parameter. Psi is what we want to integrate over to produce the Borel transform. And we see there quite easily strings of poles, which are basically here in the picture on that slide represented. I mean, they're lying on these dashed lines. The strings of poles are supported on the dashed lines in this picture. Well, what that means is we have a, say, integer infinity of choices for the ray row. So in any of these wedges where there are no poles, we can have a ray row and integrate over it. So this gives us a collection, countable infinite collection of functions f rho k that we can work with, which all have the same asymptotic expansion as is just reproduced in the way I outlined. And so, yeah, let's look at how they're related to each other. This is, of course, then, well, it's, say, it could be the function from a ray in this wedge, and we compare it to the function from a ray in this wedge. So this is the difference here. And of course, it's a straightforward exercise. Namely, what you have to do is to basically sum over the residues of the poles, which are, say, on that line here. And that gives a formula that you already may find kind of intriguing. There's a dialogue, which is perhaps kind of suggestive that appears in this formula. But yeah, it's really just a straightforward exercise. You work out poles and residues and so on and sum. What turns out to be of special interest, and of course we have arranged here a little bit. So it turns out there is a preferred wedge, which in the end of the day appears to play a special role. And if you have, with some conventions on the variables, this would correspond to just integrating along the positive real half line. And part of the technical results, about which, I mean, I don't want to speak much about technicalities, like how all these calculations are done. This is probably a little boring, but of course it took a fair amount of work. One can show from that formula here, basically, with a few steps of massaging integrals and so on, that this Borel transform can be remassaged into this nice integral, which some of you may recognize as a triple sine function. So it's reasonably sort of, it's part of a reasonably famous class of special functions. That's what we find here with this yeah, well, here you see the t, here you see the lambda, and if there's lambda check, it just means lambda over 2 pi. All right, so here I think what is more instructive is then sort of to look at the resulting picture, which is kind of neat when we look what we get after a certain amount of calculations. So for any row, right, row has this discrete infinite number of choices in the infinite number of wedges that we have seen in the previous slide. For any of those, well, we can find a decomposition of this form where we see sort of contributions of a rather different type, and that starts perhaps looking somewhat interesting. So on the one hand, we find something that doesn't depend on the choice of row. And in fact, well, if you have just a little bit of knowledge or experience with resurgence and these Stokes phenomena and so on, or summation, then of course, yeah, this is maybe what you expect. There's kind of a perturbative part, and what we find here is basically the reorganization of this perturbative series a la Gupta-Kumar-Vafa, right? So we had a divergent series, but of course it was known for a long time, how to rearrange it by sort of not viewing it as a summation over powers of lambda, but rather as a summation over powers of these e to the 2 pi I t, that you get something which has a non-zero radius of convergence and defines something. You may not like the analytic properties, but it defines something, and this is what we call the FGV for the Gupta-Kumar-Vafa part of the free energy. And again, yeah, it doesn't depend on rho. And the other part which depends on rho is, of course, well, an interesting one.
Joerg, could you associate this FGV to one of these chambers? Like or maybe the real, the ray through along the real axis that you just gave us?
You know, the point is going to be that it is universal to all the chambers. That's
sure,
the point about it.
But it's not equal to any one in any chamber, or is it?
Oh, actually it is, but okay, you're sort of make me jump ahead of myself. Okay. It is the chamber on the imaginary axis, which is of course a little degenerate. So there it is the result. And yeah, that's gonna come here. So yeah, the other part, which for, well, generic choice of rho is just what it is. So yeah, one of the key features is that it has this type of dependence on lambda and on t. So you have the characteristic 1 over lambda everywhere. And of course, yeah, this is very suggestive of non-perturbative effects in string theory. So indeed, it invites, and well, that is the only reasonable interpretation, to interpret it in terms of D-brane effects. So it's exactly what we expect, but of course here it's just the result of some calculations that we find this part, and it has the right sort of dependence and so on. And furthermore, but yeah, and here perhaps it's getting interesting, and perhaps some questions it still raises, which would be interesting to answer. So what we see is that by varying this ray rho between imaginary axis, where this D-brane part is just 0, and we're only having Gupta-Kumar-Vafa part, and the real axis, where we find this here as the result for this FD, the D-brane part, which is also something known, namely that is the Nekrasov-Shatashvili limit of the refined topological string free energy. Well, we just calculate and find it. And well, in particular, as a particular case of our results, what we obtain is a proof of a conjecture that Hatsuda Okuyama had made previously, namely that indeed the Borel summation along positive real axis gives something that you can simply define as a non-perturbative definition for topological string partition function. And they had conjectured that this thing here is equal to the thing on the right, and checked it, of course, very carefully numerically. So there was little doubt that it is correct, but okay, there was no analytic proof. Part of a result is an analytic proof, sort of as a corollary of this business of Stokes jumps. But yeah, the interest here is that this is exactly the form that Marcos Marinho and collaborators, well, going back to the pioneering paper of Hatsuda, Marinho, Moriyama, and Okuyama, had proposed as non-perturbative completion of the topological string based on the observation that, well, the FGV has as function of lambda an unsatisfactory range of analyticity, but when you add just this term, it's going to get repaired and you get something that has a much nicer and larger domain of analyticity, which was part of the reasons for, well, advocating this as a definition of the topological string partition function non-perturbatively. So here now it's a theorem that this is in fact the Borel summation along positive real axis. But in some sense, what I find the most interesting bit is really to, well, elaborate on this jumping behavior, which after all, I mean, in some sense, from our perspective, any choice of row is as good as any other, right? So there is it's a choice you can make, and they have all the same asymptotic series. So yeah, I think it makes sense to consider this more democratically, and good.
Can I ask one question?
Sure, of course.
Slide. So can I go back one slide? Yeah, so you define this the big Q prime and a small Q prime, and they don't appear in your equation, and lambda appears in the denominator in exponent. I don't know.
Oh, okay. Of course, yeah. There's a bit of a pain of maybe juggling with different notation. So, I mean, I wrote here rather explicit formula of these two parts, right? You see the FGV, which is quite explicit in terms of lambda and t.
Yes.
And we see
here G is a t.
Yeah, okay, good. You don't see it from this formula. This is what is unfortunate, but I can just well, I just need to ask you to believe me that by a resummation, you make it manifestly a function of these variables. Perhaps I'm going to have an expression somewhere later where this is more manifest. Yes, I agree.
So
it is in this form. Sorry?
The G was a lambda?
The G. Oh, okay. No, but yes, you see here we have we're defining function of G in the argument. Right. And here we're evaluating it simply with G equals lambda.
Okay.
This has, okay, well, this has some weird historical reasons.
Okay. And
well, okay. I mean, just replace G with lambda, and then everything should be clear.
Okay. And can you go back one slide to the picture? Is that so you drew many dashed lines. I assume those are poles lying on those lines?
Yeah, the poles are lying on these lines. So, I mean, okay, the picture is there. The poles are lying here with integer shifts in the imaginary part. So we have one unit of shift, another unit of shift, and so on. This is how you generate the pattern. And then one important feature is indeed that this accumulates towards the imaginary axis. So there, of course, these lines are getting dense.
And horizontally, are they all? Where are the horizontal?
Oh, I mean, well, this is basically a real life picture. So that is the full set of lines that we have there.
Okay, real life picture. Okay.
Of course, you could, with a change of parameters, maybe want to have it more beautiful by having this here tilted towards the real axis or something. Okay. And then this wouldn't be as much squeezed as it is right now. But yeah, that.
Okay. And maybe one vague question: what's the So the Gromov-Wheaton invariance has geometrical interpretation, can be computed. What's the choice of the ray corresponds to geometrically? It's kind of a vague question, but
I didn't quite get it. So what
scalars? The coefficients of the generating function are the curve counts for the Gromov-Wheaton generating function.
Yeah. My question was, what's the choice of the ray corresponds to geometrically?
No, this is going to be more complicated thing, and we're going to give perhaps different types of answers later. So that's not okay. Maybe.
Yeah, I'll wait.
Well, if you don't feel this was well answered, then maybe remind me, please.
Okay, sure. Thanks.
Okay. Okay. So yes, here is where I wanted to continue. Yeah, basically the next observation we want to make is that what we see here in the jumps is basically the spectrum of BPS states of the resolved Koni fault. This by itself is perhaps not surprise in itself, but I mean, I think the main theme is going to be sort of to elaborate on the way this is mathematically encoded, because I think this gives some hints which are really new. But yeah, the first observation, and this is still like drawing on these very explicit calculations, is that we can basically read the spectrum of BPS states from the jumps, their location, and then, well, we can even read the central charges of the BPS states from the expressions that we have obtained. So how does it work? Here, of course, yeah, I cannot introduce everything that I would need to introduce, so I would need to assume a little bit of familiarity with the theory and description of BPS states in string theory. So we have a charge lattice gathering the charges that the D-branes can have. Here, we just have two-dimensional lattice, two generators denoted delta and beta, corresponding to D0 and D2 brane respectively. The central charge functions in that case, but that is of course a feature that is not as simple in general, but is as simple here, is we have a very simple, basically linear relationship between the central charge functions, which are key characteristics of the BPS states. So giving, yeah, what we have in the commutator of supercharges in the spectrum acting on a BPS state. So it has this very simple formula, and that is pretty well known for the resolved Koni fault. And then, well, one of the main questions in the business is for which charges gamma do there actually exist stable BPS states in the spectrum? And here's the answer that is also well known. Well, okay, actually I missed to give references here in mathematics. That is Joyce and Song, I believe, and Mina can probably quickly tell me what the physics origin is. So these are the BPS indices telling me for which, I mean, it's a weighted count with some signs of the BPS states that exist for given charges. So that is the result here very explicitly. So we have here these types of charges with a 1. And this is exactly sort of what then corresponds basically to the lines here. And then there's a -2, which would correspond basically to the imaginary axis here, where there's this accumulation, and in some sense, well, that there's a -2 is related to the appearance of this accumulation. And that's it. So it's a very simple example.
Joerg, just a stupid question. The plane that you were drawing, originally it came from this Borel transform. I'm a little bit confused about the meaning. There's of course a central charge plane, but that's not the same plane as the
okay, yeah.
Is this stability of like stability conditions, like on moduli space of
that's exactly it. And I'm about to get there, right? So that's the next slide to introduce the stability space, because the stability space in this case basically is going to be parameterized by, yeah, I mean, there's some subtleties having to do with C star actions and so on, which I'm probably not going to fully elaborate. But, yeah.
Can we just go back and just walk us through how you got the picture in the simple example, that picture? On the is this a complex zeta plane, or it's a z tau plane, or zeta tau? What is this?
Okay, yeah, no, thanks. Now I'm getting what is the point. So we have, you see, of course, here it was about sort of where we can integrate. But when you think about sort of this Laplace transform, then you see that basically if, I mean, what these lines in the psi plane correspond to will also be the lines in the, I mean, you have a correspondence between the rays in the lambda plane and the lines or wedges or sectors in the psi plane. simply because you have this ratio here, right? So therefore you have basically the same picture in the lambda plane. So just I'm inviting you to here replace the label psi by lambda, and then you have the picture of jumps that this function here produces, or that this Laplace transform produces in the lambda plane when you vary the choice of row between here one sector or one chamber to another. Okay.
Great. And in that formula, we're taking t to be real. Sorry, in the picture, you're taking.
So in this formula, no, we're giving t in fact some imaginary, well, some real value, and the imaginary part is of course what gives the Kähler parameter in our conventions. And so what produces this little tilt here is that we have a non-vanishing real part of t.
Okay.
Right. There is of course,
okay.
yeah, I mean, yeah. Okay, that's it.
Thanks.
Good. So simply here, what I wanted to point out, or what I wanted to get at, is that this formula for the jumps, now sort of written in a universal form, which holds for all the rays where there are jumps, and all the, which are then via the central charge function are related to no, okay, so here it says functions of lambda, and good, there is, okay, how to say it. So I want to say, and I want to say that basically we can rewrite the generic formula for the jumps, where indeed I have to hide several technicalities. So this here is of course obvious for the lines here, which are the jumps, which are kind of most obvious. There's some subtle accumulation of jumps on the imaginary axis. And in order to get that right, fully right, you really need to take into account everything, including the constant map contribution. And that's a little, I mean, it's kind of fun to see how it works out ultimately, but yeah, in the end of the day, there is really this universal formula for the jumps, which can be expressed in terms of really just the data of the BPS states with the z gamma of t appearing here in the argument. So, and the omega of gamma, the BPS index, basically giving the multiplicity with which this jump appears. So that's, well, that's just a rewriting after a couple of steps. And that of course is suggestive, and in particular it allows us to maybe strengthen a little bit the interpretation, but here I think more is to be explained and clarified. So I mean, the interpretation in terms of D-branes was of course based on this standard law and on the observed clear matches with between just the data and the functions and the patterns and so on, with what we know is the spectrum of BPS brains. So this gives basically then this thing. But what I don't know actually is whether there exists a first principle, say, worldsheet explanation of that very formula. That I think would be a very interesting question. I mean, it seems pretty clear that these effects that we have found here, these FD, they must have to do with the D-branes. I think that is kind of obvious, just from the type of dependence that we have and so on. And of course, we have some idea what they should be related to, which is they should be coming from disk amplitudes where the boundaries are represented by the stable D-branes. That is the type of non-perturbative effects that we expect in this context. And we can furthermore see that sort of this jumping behavior has to do with sort of D-branes moving. I mean, the sum that is being performed here in going basically between real and imaginary axis, that is going to be the sum over all jumps. And well, this depends then now on the, for example, here, the real part of T, whether, for example, this line will move to the upper half plane or not. So this is what would change the, yeah, you may want to call it framed wall crossing in the formula here. And well, I think it would be interesting to clarify sort of how this formula, or if this formula can be obtained sort of from really a detailed analysis of, say, non-perturbative d-brane effects with, I mean, something like open Gromov-Wittens with the boundaries associated to these d-branes. But yeah, this is just, I mean, actually, I was hoping that perhaps Mina can tell me the answer straight away, but this is, for the moment, well, we're just making observations on the basis of our Borel summation results. Good. I think, well, for the rest of this talk, what I want to elaborate on is math and the sort of mathematical interpretation of the type of formula that we have in relation to geometry and in relation to some geometry suggested to be attached to this problem previously. So for this, I need to introduce a few notations or definitions. So there is something called the space of stability conditions. So, well, d-branes, they are, or the spectrum of d-branes is known to be locally constant, but can jump across lines of marginal stability. And this has led, after a long series of efforts, to the notion of the space of stability conditions. What is, well, the very basic structure is that one starts with this well, a complex manifold. That's what this space is supposed to be, or which we fiber the charge lattices, giving the charges of the d-branes. Well, to just introduce the necessary notations, we assume, or that is basically a consequence of the axioms, that then locally we can find local charts for B covering this complex manifold such that in the local chart one can have basis for the charge lattice, which basically bring the intersection pairing to the standard form. So this is how we denote sort of the vectors of that basis. And then the space is supposed to have local coordinates. I mean, these charts are supposed to have local coordinates for the space B, which ultimately, of course, in physics, we want to identify with the central charge functions. But well, to the best of my knowledge, in this axiomatic version of that story that Tom Bridgelin has associated to the general, well, abstract formulation of BPS states in terms of some generalized DT invariants, well, these are just some complex coordinates for that base B. There's, well, there's in fact some, I think, open problems to the best of my knowledge as to the precise relation between the math version of these stability spaces and then what we believe to be relevant in physics, which is in particular the space of complex structures, or in the context we're in, that is A model Kähler structures. Anyway, Tom Bridgelin likes to then consider also the tangent bundle over that space with the coordinates that we just denote by capital thetas. So what would that be in our example? Well, it will correspond to, on the one hand, one needs to double the charge lattice. So where previously the Z, so from associated to the D2s and D0s, just here the first part, but now it's going to be completed by basically some, well, pseudo D4 and D6 charge, which are pseudo because we're in a non-compact situation. So that would be the pattern that would have in a, well, dimension 1 moduli space compact Calabi-Yau, but if we think of the Koni fold as being obtained by some decompactification limit, then D6 and D4 would become non-compact and would account here for these extra generators of the charge lattice. One associates central charge functions to the D0 and to the D2. But of course, there's a C star symmetry allows us to scale those. And in the end of the day, really what is physically relevant are going to be the ratios or homogeneous coordinates. And then you can associate, in this case, with a little bit of ambiguity, but some basically dual partners, Z0 check and Z1 check, which are determined by special geometry or the choice of a prepotential. So that is the setup that is in particular exactly the setup that Tom Bridgeland has used in order to set up a Riemann-Hilbert problem for the case of the resolved Koni fault, which is exactly the one that we're looking at now. Well, the point is somehow to, or the vision is to encode everything in geometry. And the way the geometry is constructed is really beautiful, because one starts with this as basically the starting point. So one has this atlas for B and so on. But this is not going to be a very good complex manifold, for the reason that when central charge functions vanish, there are discriminant loci and so on. One can try to repair this as a complex manifold by introducing better coordinates. And these are defined by a formalism, which in the gauge theory context was introduced by Gayotto Murnaitske, and Tom Bridgeland has basically set up a purely complex version and refined it mathematically for the cases at hand. So yeah, the point is basically to go from this, so to pass to a twistor space, which is this total space of the tangent bundle that we looked at times a C star. So there's a twistor parameter zeta being introduced to that aim, and then to seek coordinates for that twistor space, defining basically for each fixed value of the twistor parameter a complex structure. So in other words, we're defining a hypercomplex structure in this way by basically introducing the coordinates explicitly. Well, not quite explicitly, we're introducing the coordinates defining the complex structure as solution to this BPS Riemann-Hilbert problem, which has two main ingredients. On the one hand, what we're saying, maybe let's start here at the bottom, we're specifying the relation between the coordinates here, lowercase x, which are obtained, which are related to the uppercase x here by exponentiation, and the central charge functions like that. So they give the leading asymptotics in the zeta to 0 limit. So this gives the central charge functions, and then somewhat interestingly, the capital thetas appear sort of as next to leading order, and then there's higher orders. So this is sort of the boundary conditions relating the new coordinates to the old coordinates, which were the central charge functions and the thetas. But then, yeah, the main thing or the main meat is in the way sort of the adjacent patches are glued to each other, the changes of coordinates formulae, which are of these cluster algebra types, where we see, well, the key ingredients characterizing the BPS spectrum basically as the main data defining these formulae. Namely, there's the intersection pairing and there's the BPS indices. And when these are given, when these are known, then we have the full system of coordinate changes. So thereby, we can define, postulating this to be the transition functions, we're defining the complex structure. And well, then the problem to find for given z, for given omega, and so on, these functions x, which are going to be complicated functions of zeta and the central charge functions, that is basically, well, the Riemann-Hilbert problem that Bridgeland has proposed us to consider. It is, of course, very closely related to similar things that Gayotto Murnaitske have studied. The differences here in this asymptotic behavior, which in their context, Gayotto Murnaitske had non-holomorphic terms. So the crucial difference is that this is purely holomorphic. There's a limit called conformal limit relating the two. Anyway, so here comes sort of the main statement of results of how all this business is related to our Borel summation results. Namely, the main point is that basically, well, there is a associated to this complex manifold, there is a natural, in fact, you could call it canonical holomorphic, or in fact hyperholomorphic, because it is holomorphic for any value of zeta line bundle on this twistor space, with the transition functions being just the exponentials of the Stokes jumps that we have computed. Secondly, but this is of course kind of a triviality or tautology in the setup we're working, is that holomorphic sections of this line bundle are the partition functions we're talking about. So for the different rows, we basically have different charts, and then the transition from one chart to another is the jump, and that is the guy up here. But yeah, in some sense, well, this is also, in some sense, parts 1 and 2 are kind of void of content. The real content is perhaps here, part 3. Namely, we can check that, in fact, the guys that we found here by explicit calculation are difference generating functions of the changes of Darboux coordinates. What that means is, okay, you take here, say, the Z0 shifted by 1, and divide by the guy unshifted, out comes the right-hand side specialized sort of to the Koni fold case of that change of coordinates formula. And that I think is quite remarkable. So basically it says that these guys that we find here are uniquely determined, are canonically determined just by this type of peculiar complex geometry that we're defining here. Sort of for free, we're getting as a bonus feature here our generating functions, and these, of course, we can use. We're always free to use them to define then a line bundle over our twistor space. Yes, to my mind, still remarkable thing is that we see that this is the same thing as the Stokes jumps. In some sense, of course, I mean, here we're coming to the origin of the whole project because we had observed something very similar in a previous project with Joanna Koman, Pietro Longhi, a bit more than a year ago, and I've had the pleasure to present this in basically the same seminar. So we saw something very similar in another class of examples, which are basically the local Calabi-Yau's relevant for class S, for geometric engineering of class S. So we saw somehow that there is a interesting global structure. There were these tau functions, and the changes of tau function from chart to chart were represented by difference generating functions of Darboux coordinates of a very similar type here. It's not quite the same context we're in, but anyway, it was formally very similar. And basically the underlying question of this project I'm discussing here was whether it has any chance to generalize to, for example, toric Calabi-Yau's. And well, answer clearly is yes for Koni fold, but I believe this is not going to be the end of the story. And yeah, second remark is also what we sort of at the end of our project with Joanna and Pietro observed was that this kind of picture is actually something that with very different type of reasoning and very different type of background had been proposed before by Alexandrov, Persson-Piolin and Andy Neitzke, who had considered in the context of hypermultiplet moduli spaces and the QK-HK correspondence that plays an important role for characterizing the quaternion-Killer metrics of these hypermultiplet moduli spaces. They were led to consider, well, an basically enhanced version of this formalism of Galiotto-Moore-Neitzke, and there is a hyperholomorphic line bundle playing a crucial role there. And based on basically some observations related to M1OP conjecture, Alexandrov, Persson-Piolin even had put forward a conjecture that this is related to the topological string partition functions. In some sense, what, well, our previous work and this work then provides are very concrete cases where there's a detailed proof of such a statement of this proposal that they made. I view, however, sort of the link to their formalism really as a crucial hint for future developments. I think indeed this is sort of the right framework for further developing the subject and generalizing this. I think here really this is sort of where the deep theory is going to come from. Anyway, so yeah, that is all weak coupling, right? However, and let me see how I'm doing with time. Maybe 10 minutes may be okay to get to some conclusion, I hope. I want to say something about strong coupling as well, right? Because that should be interesting. Strong coupling means so far lambda basically was sent to 0. But what we discovered in the course of our project is that, I mean, without much of pain, we can use the ideas and methods that were developed for all this Borel summation and so on to massage the formulae for the non-perturbative completion of the topological string into a form like this, where here, I mean, previously we had here 1 over lambda, but now you see here multiplication with lambda. So this is the type of Laplace transform that you want to have if you want to understand the lambda to infinity behavior. Okay, I mean, that's again just a calculation. We see something that looks quite similar. So again, there's a Borel transform here, which is represented as an infinite series. Perhaps what you may already, with a bit of experience, anticipate, there's something interesting here with the variables happening. T, basically the role of T is taken by T prime and so on. Anyway, I will come back to this. Of course, yeah, you can just take this formula, you can then expand in powers of V, integrate termwise, so this gives you a strong coupling expansion. However, now you can, of course, ask or play a very similar game, right? So you can then ask, well, here we have a specific ray and a specific contour of integration, but what if we play with it? Because, of course, what you can say very easily, the pattern of poles and so on of the strong coupling Borel transform is very similar, but not identical, because there's these important changes of variables to the one we've seen before. But the story basically proceeds in some analogy. And yeah, what you find is that then sort of these Borel summations, which are now sort of the different strong coupling resummations, have a similar structure like here, where now it is the FNS, right? These were previously the D-brane effects which jumped at weak coupling, but now they're kept fixed. They're not dependent on the strong coupling ray, but this guy jumps. For a particular, I mean, for one particular choice of ray, we know already what the result is, because then we know the FBPS, that's how we call this guy that was now produced here, must reproduce the F Kupakuma Wafa. But now what are the others? Well, here's the result. So, I mean, these are basically the Donaldson-Thomas partition functions, which are defined as the generating functions of BPS indices. Here, well, these are the BPS indices for D0, D2, D6 bound states. So that is, of course, a very famous and much studied object here. The delta check would correspond to the D6. And of course, it's well known that these guys are locally constant with respect to Kähler moduli, but jump across walls of marginal stability. So these guys in general depend on a choice of chamber in Kähler moduli space. In the large volume chamber, so there's a distinguished chamber. Well, the one where we have here FBPS is FGV. That corresponds to the integral along real axis. There we can, well, these guys are famously known to be related to the FGV. So this gives us in particular the dictionary between variables here. So we can relate, yeah, it gives the dictionary between variables, maybe details I should not talk too much about in view of time. But yeah, then on the other hand, well, Jafferis and Moore have worked out basically this function here for all the possible chambers for the resolved Koni fault. There was then a little later some mathematical work by Nagao and Nakajima working out the wall crossing formula for this guy here, and thereby also computing and reproducing, of course, Jafferis-Moore's result for the Donaldson-Thomas partition function. We also matched parameters. So with our lambda and our t in our conventions, well, there's in the end a very simple relation, namely the ZBPS now viewed as function of the choice of strong coupling ray. I mean, this dictionary implies in particular a very simple relation between the chambers of Jafferis-Moore and the wedges in our ray diagram. I think Marinho calls it peacock diagram, which then gives this result chamber by chamber, or whenever the ray rho prime is, after application of the dictionary we found here, in the chamber, this is identically true. All right, so yeah. Well, I think, yes, maybe let me say, at least in 1 minute, one of the things I personally found the most striking about these results, and this was really, I think, this is from the point of view of trying to understand the kind of mathematical framework behind, I view it as a really very important clue that sort of from this example can be extracted. Namely, there was on the one hand sort of these, we had these Bridgeland-Riemann-Hilbert problems, which seemed to capture important aspects of the story through the relation between here these partition functions and their jumps basically being the transition functions of this canonical line bundle. So that in some sense is a first small upgrade of the context that Tom Bridgeland had envisaged. But now, I think he didn't really think much about then lambda going to infinity. What we find is that basically the behavior there is governed by a dual Riemann-Hilbert problem. And so basically, okay, where the weak coupling variables x, capital X0, capital X1, now there's they all have partners obtained by basically very simple replacements. So it's basically the replacement of Z0 by zeta, the twistor parameter, which happens. But yeah, I mean, of course, this of course will affect all the jump formulae and so on. So these guys will also have jumps of this cluster algebra type. And if you then study this, I mean, how they are related to our Stokes jumps of the strong coupling expansion, then the ultimate upshot is that, again, there's a very simple relation, namely the Stokes jumps of ZBPS turn out to be the jumps as determined by the dual Riemann-Hilbert problem of a particular coordinate, namely the coordinate x0 prime. So that is basically the conjugate to the coordinate associated to the D0 charge. So there's a distinguished coordinate which just by the very definition, by the very formulation of Riemann-Hilbert problems of this type, will have the jumps that we find from the Stokes phenomena. And I believe here...
the D6 branch chart, right?
Yeah. That is related to the D6.
Formally define, or how do you define it?
Well, if you want by, okay, I mean, here it's just sort of formally introduced by, I mean, in a sense by fiat, but of course you can motivate it from string theory by thinking of it as a decompactification limit of something compact, right? So, and of course, the D6 that we're talking about here, the delta check charge, I mean, this is, well, that is the infinitely heavy D6 that, of course, in the context of MNOP and all this was considered, which produces the framing basically here, allowing us to define the framed BPS indices that are being counted there, right? So it's just that old story that we're coming back to. Yeah. I mean, is it what you wanted to?
I mean, it's just that if you actually want to think about variation of stability condition, right, then it has to be an actual function that, you know, depending on its particular angle, it will actually tell you whether things do or do not bind, like actually so, not simply.
Yeah, I mean,
so it has to be a real thing.
Sure. I mean, okay, so what we're talking about here, just to be clear and precise, is framed wall crossing. And it is the wall crossing, say, of, I mean, like what Jafarius and Moore have studied, that from the bound states of D0, D2, D6, you can separate off or, well, split off some D2, D0 bound states. And this is what this wall crossing describes. And this is what these jumps that we see here correspond to. Yeah. Good. To end this slide, and this almost ends the talk then, I think then, yes, I'm really running out of time. Let us note that, of course, one should, in order to get back to the physical variables, which are lambda and t, or then lambda prime and t prime. So this kind of dualization recipe here in terms of, say, the coordinates like central charge, which have the C star action, and the twistor parameter, which there was just the exchange of zeta and z0. In terms of lambda and t, the dualization will correspond to these formulae, namely it's the replacement of lambda going to lambda prime, given by this formula, and t prime, given by this formula, where there's 1 over lambda very importantly appearing. And this is something that people have seen before, namely that basically is related to how S duality is realized on coordinates of hypermultiplet moduli spaces. So this basically here comes for free from the maths of Stokes phenomena in the resummation. And yes, so indeed, basically, well, the interpretation it invites us to adopt is that we start seeing here some hints as to how mathematically the S duality should be realized in this framework by basically the passage from Riemann-Hilbert problem to dual Riemann-Hilbert problem. Anyway, I think I should finish. So this is the conclusion slide. So let me just stress to conclude that the original series, which was defined entirely in terms of Gromov-Witten invariants, knew everything, right? Everything what we have seen here is just repackaging of the information of that formal series we started from. And that, of course, is if you like, a nice illustration of this general theme of resurgence. So it basically tells sort of how much this and well, all the non-perturbative completions know about all these kinds of non-perturbative effects, where we have sort of these two types, right? We had non-perturbative effects at weak coupling related to the well, mathematically, these canonical line bundles, hypermultiplet moduli spaces, and so on, and physically related to d-branes, disk amplitudes, and the like. And yes, I think it would be interesting sort of to clarify precisely how this type of framed wall crossing that we observe here is really predicted by the well, wordsheet approach. But at strong coupling, there are other Stokes jumps. They have other positions and they have other mathematical realization, and that is mathematically described by the dual Riemann-Hilbert problem of Bridgeland type. And we had observed, or we have made observations indicating relation to the S duality. All right, so in some sense, yeah, there's these two types of jumps and there's the two types of expansions, and they have, well, there's different math and, well, different, but of course not unrelated math and physics associated to it. So there's framed wall crossing sort of in Gromov-Witten theory or open Gromov-Witten theory or something like that. So I would really like to have this clarified, and Donaldson-Thomas theory at strong coupling. Okay, and yeah, let me just end with the hope that we have seen glimpses of maybe a well, unified picture that applies to much larger classes of examples. Thanks.
Thanks, Joerg.
Okay, so do we have questions?
I have some questions if others don't, but let's see. Maybe others go first.
So for derived, so like in the mathematical formalism of stability conditions, you're studying the derived category of usually like a variety, And you want to have a good handle on the K theory and the derived categories, so that you can compute the K theory of a variety in some cases just algebraically, but a lot of the time it's like almost infinite sequences of coherent sheaves on the variety, like classes of them. So it's it's kind of hard to do to compute the space of Bridgeland stability conditions explicitly. In a lot of cases.
I am aware of this fact. This is relatively far from my expertise, but I can at least assure you that in this case we're in good shape. So what was here stated as a result for the BPS indices is an example in this long work of Joyce and Song.
Right.
So that is sort of what I would refer to for sort of the math scores.
So I first have a question. So is it not possible to think of the lambda plane as like a P1, just compactified, and have a single problem as opposed to two different problems?
Yes, actually, no, this is an excellent question. And in a sense, you're absolutely right. There is, good. No, this is really a very interesting point. Good that you sort of made me say a few words about it. I had to be brutally quick here at some places, right? So, and in particular, now looking at it, this formulation or this version of, say, the Bridgeland's Riemann-Hilbert problem, in fact, is incomplete. Bridgeland does have an assumption on the behavior for zeta to infinity. And that is important. That is important in order to ensure uniqueness of a solution. So he proves that when sort of the behavior at infinity is of polynomial type, so there's not more than polynomial growth, then this type of Riemann-Hilbert problem in fact has a unique solution. What that says is that in fact, the weak coupling, say, let's call it the weak coupling Riemann-Hilbert problem, does the job. It defines the thing. And it spits out the functions that we have now computed in a different way by this Borel summation business. I mean, this is just what, the comparison gives. On the other hand, he wasn't studying more explicitly the strong coupling behavior. And I think the more precise or the better way of saying it is that you could have equally well characterized all the objects in terms of the strong coupling Riemann-Hilbert problem, which has a very similar shape with slightly modified asymptotic behavior, etc., etc. It would have defined the same functions. What is, however, also interesting is, to look at sort of the pattern of chambers that emerges, right? So we have on the one hand, the weak coupling gives us in some sense this peacock or ray pattern around the, say, North Pole. That of course you can try to continue all the way to the strong coupling. If you, however, then want to draw in that picture the rays that you get in the strong coupling expansion, what modifies things quite a bit is that the lambda appears in this relation. So this means that in fact, what used to be rays, so the strong, what are rays sort of in the strong coupling variables become in the weak coupling variables, in fact, these are parallels to the imaginary axis. So what that means is that in fact, you have a kind of intricate global structure where you can, if you want, decompose vicinities of North and South Pole according to strong and weak coupling peacock ray patterns. But of course, you can then tile the whole C star by these rays, these jumps. And there is then distinguished wedge, a kind of self-dual wedge, where you make the transition, and well, guess what is associated to it? The non-perturbative partition function of Marinho and company. So it seems that also from that point of view, from the point of view of geometry, there is kind of this distinguished kind of self-dual chamber in which you most simply make the transition between strong and weak coupling, or where the transition between strong and weak coupling is the simplest. But I think, yes, all this is sort of part of, I think, the picture that, well, that starts, well, emerging here.
I think too, well, what should be true is that basically the brane central charges have complete information about perturbative string theory, and in some sense we know that. And I think this is true in I think almost any generality we want. It's true when you have a Calabi-Yau manifold, because we know that we can, in principle, reconstruct from genus 0 data all higher genus amplitudes, and in turn you get to construct those from period integrals. So the period integrals know everything. In other words, the central charges themselves. And so what's also true is that the behavior of those central charges, namely the pi stability central charge, knows everything that happens in the derived category. Sorry, the other way around. Sorry, when interesting things happen to the brane central charges, it's also when the relation between brane central charges have to capture changes of stability condition in the derived category, simply because they know everything about a K-theory of branes, and that has to like move together, right? So if you get to be in some chamber where a certain brane becomes unstable and it's better to write it in terms of some other branes, the central charges know this.
Mm-hmm.
So what? Well, probably.
I mean, I think in spirit, I completely agree. The question would be somehow how exactly this is kind of taken into account in this mathematically, sort of in this framework or in this context.
Well, in some sense, what you're doing, right, is you're studying analytic continuation type problems, right? How do we take a perturbative expansion and make it into an analytic function, right?
Mm-hmm.
And sort of a good analytic expansion are given in terms of stable objects. So you simply write your the wall crossings capture this change of coordinates from one chamber to the next that tells you what are sort of the good coordinates, the good light branes in terms of which you want to write everything else.
Mm-hmm, mm-hmm, mm-hmm.
Yeah, so I think your two problems have to be related. And also, I think when you're studying this, the conifold story, yeah, okay. There's sort of a natural deformation which will regularize the central charges of everything, and the problem should become nicer because it will break the sort of the ugly asymmetry between D6, D4, and everything else, which is simply you work equivariant, you turn on equivariant parameters, which you can do in topological string. Mm-hmm. And this won't break anything. It will just regularize everything in sort of a nice way. So I think you have everything. And you have this nice moduli space, which has a physical, I suppose, interpretation, right, as the actual moduli of the four-dimensional theory, sorry, of the three-dimensional theory, again, by compactifying the 4D string theory to three dimensions on a circle, right? Where I think you're there. It sounds like you essentially have the whole story, but it should be one story. I don't think you have, as you said, I think you've got it all. It's one story.
Yeah, I think what is really becoming visible, but well, some more work will be needed to flesh it out, is the, I believe, correct mathematical framework to somehow, well, get all these things, these non-perturbative things from geometry, namely the geometry of spaces of stability conditions / hypermultiplet moduli spaces in string theory. There's, by the way, yes, there are, okay, well, you're kind of provoking me to add a few more remarks, namely, maybe two. So on the one hand, I think what is, I think, quite within reach, and perhaps, I mean, I'm quite optimistic that one can do it in finite, maybe relatively small time. Say for local Calabi-Yau, including these, I mean, compact D6, the D4s, I think the story basically should work. I mean, should follow really the same pattern. So that is, that should be really relatively immediate. That was sort of maybe remark number one. The other is, I think there was for a long time some interesting confusion as to the relation of these space that Bridgeland liked to talk about, his space of stability conditions, and their sort of physical moduli spaces, right? It seemed to be too large, and it wasn't quite clear sort of how to cut out the right one. And yeah, I mean, this has in fact been the subject of some discussion of Tom and myself. Basically, really, it is the story whether you want to here start with independent complex coordinates. This is what sort of in the complex hyperkähler geometry and so on that Tom has started from would be what you consider. Or you can you may want, and that is sort of what I think for a physicist immediate, simply impose special geometry relations expressing the z checks in terms of the z's. What is a non-trivial question then, if assuming that sort of in the complex world you have a solution of the Riemann-Hilbert problem, whether it survives the restriction sort of to the good Lagrangian slices, which are defined by these special geometry relations. And this again has to do, I think, quite remarkably and quite profoundly with this question, what happens at zeta to infinity? I mean, the question indeed, which is non-trivial in general, if you think about sort of just generally imposing any conditions like that, then a solution to the Riemann-Hilbert problem that has these good properties may not need to define a solution to the Riemann-Hilbert problem having all these good properties after imposing this restriction for some reason. Okay, I could explain, but that is technical and would take a moment. So in other words, there is sort of, well, I mean, those conditions that string theory likes, probably due to S-duality, are those that make the thing work, right? So that ensure a good strong coupling behavior on the one hand, and well, therefore ensure the realization of S-duality that we expect string theory to have on the other hand. There indeed seems to be, I mean, again, we're in some respects maybe at the beginning, but I think, yeah, the outlines of the picture are there.
Are there more questions? Okay, if there are no more questions, let us thank Joerg again. Thank you for a very nice talk.
Yeah, thank you for the invitation.
Yeah, and everyone else, if you are around in Berkeley, feel free to join us right now in the interaction area for some sandwiches. Yeah, thank you very much, Joerg.
Okay, enjoy your food. For me, it's time to go to bed. I have to get up at 5:45 tomorrow. And okay, anyway, thanks again. Have a nice day, and see you some other time, I hope. Bye-bye.
Goodbye.